effective mass m star. Let electron of charge E and mass m moving inside a crystal lattice of electric field E, acceleration A is equal to E by m is not a constant in the periodic lattice of the crystal. It can be, it can be considered that its variation is caused by the variation of electron's mass when it moves in the crystal lattice. Because acceleration of the electron changes, because when it approaches positive ion, it will have some different potential energy. When it is in between two ions, it will have some other potential energy. That is the reason it will have varying electron mass. Acceleration A is equal to E by m star. Electrical force on the electron, F is equal to ma. Okay, F is equal to, instead of ma we write m star A. So effective mass of the electron E is equal to, E is equal to d square E by d square, dk square. Effective mass is determined by d square E by dk square. M star is equal to h square by d square E by dk square. We got? We got E is equal to h nu, and then all these things we applied, and then we derived this equation. Effective mass of the electron. M versus K diagram, variation of E with a K. Okay, energy, effective mass of mass and Fk as a function of K. See, you see A, B, C, D, 4 different diagrams are given here. Variation of E with K corresponds to first preloving zone. Using this type of variation, velocity can be calculated. Variation of E with respect to K is on x-axis. The other value is on, E is on y-axis. So using this variation, variation of velocity can be calculated. So variation of V with K, for K is equal to 0, velocity is actually 0, and K value increases, V also increases, reaching its maximum value at K naught, known as point of inflection. So beyond K naught, velocity decreases and reaches 0 at K is equal to pi by A. This is about this one, B diagram. And C diagram, what is actually it is saying? That near K is equal to 0, M star is equal to M. As K value increases, M star also increases, reaching its maximum value at K naught. So above K naught, M star is negative and decreases as K tends to pi by A. Beyond K naught, velocity decreases, and hence retarding force acts on the electron and behaves as a positively charged particle, referred to as hole. So variation of F of K, this is about 4th diagram here that is shown. Degree of freedom of an electron is defined as F of K is equal to M by M star. Fk is actually measure of the extent to which the electron is free in a state K. Okay. So if M star is large, effective mass of the electron is large, Fk is small. Particle behaves as heavy particle. Okay. If Fk is equal to 1, electron behaves as free electron. Okay. So this is all about, when electron is in between two positive ions, or it is when it is approaching positive ion, what will happen? When it is approaching positive ion, what will happen? Potential energy will be 0. When it approaches, when it is in between, halfway between two positive ions, then potential energy will be maximum. See here, origin of energy bands in solids. If you see, an isolated atom possesses discrete energies of different electrons. Suppose two isolated atoms are brought to very close proximity, then the electrons in the orbits of two atoms interact with each other. So at the place of each energy level, a closely spaced two energy levels exist. That's what I showed you as earlier, that electrons, when two atoms are interacting, the energy levels will get splitted into, single energy levels get splitted into two. If three atoms come together, one energy level gets splitted into three. If n number of atoms are brought together, then you see n closely spaced energy levels in place of discrete energy levels. You will see this, it is known as bands of allowed energies. The band corresponding to outermost orbits is called conduction band. The band corresponding to outermost orbit is called conduction band, and the next inner band is called valence band. So the gap between these two is actually called forbidden energy gap. That is EG. That is EG. In case of conductors, the band gap is very small, almost nil you can say. For insulators, it is very much high. For semiconductors, it is in between conductors and insulators. That is, for semiconductors, it is between 1 to 3 electron volts. See here, you see valency band, conduction band. In between band gap is there. Okay. Bands are composed of closely spaced orbitals. You can see here, for insulator, valency band and conduction band, energy gap is very much high. That's why in diamond, it is very much high, like greater than 6 electron volts, valency band and conduction band gap. In case of semiconductor, you know, Fermi energy or Fermi level exactly lies at the center of the energy gap. See, valency band and conduction band, if they are separated by Eg, Fermi level exactly at the center, you can see. In case of conduction band and valency band, it is overlapped. See, you can see overlapping of Fermi level, you can see conduction band and the valency band. Very little amount of energy is sufficient to excite electrons to conduction band in case of this one. So we are done with this chapter.